Here's another question about probability and variance and expectations. And we'll use this property, or a related property rather, when we talk about ensembles. So here's this definition of the variance. The question is it true that if these random variables all have the same variance, then if we compute the average over this set of random variables, that we have this property that we can pull out the 1 over n squared. And we can either prove or disprove this property by looking at the way that variances work when we're dealing with a sum, because it should be pretty straightforward to show that if you have a constant multiple of a random variable, then the variance of c times that x, well, that's going to be, let's use this definition on the right-hand side here. Well, that's just the expected value of cx squared minus expected value of cx squared. And the c's, they get squared, and then we just get c squared times expected value of x squared minus expected value of x squared. So we get c squared var of x. So you can kind of see where this square term is coming from. So the question is, how can we break down the variance of x plus y, and is this equal to the variance of x plus the variance of y? And what other terms might we have here? So that brings us to another quantity that we need to discuss first, which is the covariance of two random variables. So the covariance of two random variables, they are defined as follows. One way you can think about the covariance is, how much do these two variables co-vary or vary together? So if this is my range of the range of values that x could take, this is a range of values that y could take, and I sample from their joint distribution, and I get something like this, where the value of x tends to be high when the value of y is also high, then the covariance here is between these two variables are going to be large and positive, so closer to 1 and positive. Whereas if my value of x, if I sample from the joint distribution x, y, and when x is large, y tends to be small, then my covariance is going to be large but negative, so maybe close to 1 but negative. And finally, here's another case where maybe my x and y are just unrelated to each other at all, and having a large value of x, well, that doesn't really tell me anything about y. Well, then the covariance of x and y will tend to be close to 0. So let's look at this example then. Let's see, is it true that for random variables x and y, we can have this quantity, and hopefully you can work out how this relates to the problem that we've given you. So let's take a look. So we're trying to compute the variance of x plus y, and so one good place to start is just the definition of the variance. So that's just going to be x plus y minus the expected value of x plus y all squared. And I can, I'm just going to expand out the expected value and shift this a little bit. So I'm going to write within this square, I'm going to pull out my x and my expected value of x. And then I will have in red my y and expected value of y. All right, and then what I'm going to do is I'm going to expand out the square, keeping the green part together and the red part together. So that's going to be expected value of x minus expected value of x squared. There's going to be the y minus the expected value of y squared. And then I'm going to have some cross terms. So 2 times x minus expected value of x, y minus the expected value of y. So that's all good so far. And I am going to use the linearity of expectations. I'm going to have 3 terms here. Expected value, so the green term, I am going to have the red term, and then I'm going to have my final term, this black term, 2 times the expected value of x minus e to the x. I've also pulled the 2 out of the expectation, times y minus the expected value of y. All right, so now let's take a look. So this term here, well, that's just the variance of x. This red term, that's the variance of y. And I actually have a third term here, which is 2 times, and would you look at that? That's just the covariance of x and y. So it is not true in general that for these random variables x and y, it is not true that we'll have this property, but we will have this property if my covariance term happens to be 0.